Hello everyone, and welcome back to another math video. In this video, we are going to talk about derivatives and how we can use derivatives to figure out the shape of the graph. So let's get started. We know that when we talk about the first derivative will tell us about slope of the tangent line. So if let's just think about a generic function here. I'll call this guy f of x. So if the derivative tells us the slope of the tangent line, could we use that slope to help us know what's happening with a function? We're thinking about doing this without a calculator. We don't want to look at the graph. We want to know what's happening without graphing the function. So if I look at slopes of tangent lines over here on this side of the graph, you can see how all of those are going to have a positive slope. So if that slope is positive, which means it's greater than 0, you can see how that indicates the function is going to be increasing. Now, on this side, right here, if you think about all those little slopes, they're all going to be negative. So if the slope, the value of the derivative is negative, so it's less than 0, then that tells us the function is decreasing. And then we know when it's equal to 0, then we have critical numbers, and there could be a maximum or a minimum. Remember, that could also happen if that derivative is undefined. And that's really what's going on with this thing called the first derivative test. So we're looking at a function that's continuous over some interval, and we're going to have critical points within that interval. Now, if the sign changes from positive to negative, which is what's going on this piece of the graph here, if I change from positive slopes to negative slopes, which means the value of the derivative is increasing or is positive than negative, so we're increasing and decreasing, at that point in change, we're going to have a maximum value. If we go from decreasing to increasing, then at that point in change, we're going to have a minimum value. So, and this is really what's going on with this thing called the first derivative test. So let's talk about how would we conduct a first derivative test. What are your steps? Your first step is to find critical numbers. So we're going to do that in this problem. We're going to take that derivative. So I get 3x squared minus 6 times x minus 9. And then we're going to set it equal to 0. So I'm going to factor a 3 out. Oops. And I'm going to divide by 3, so that's why my 3 is gone there. And this factors into x minus 3 times x plus 1. So I've got two critical numbers. One of them is at -1, and one of them is at 3. I also need to think about where that derivative is undefined. And that derivative is not undefined anywhere. It's defined for every y value because we ended up with a quadratic for the derivative. So that's your first step. Find critical numbers. Where is the derivative equal to 0 and where is the derivative undefined? Second thing you're going to do is you're going to create this thing called a sign chart. And we're doing a sign chart for the first derivative, so I'm going to label it. That sign chart is going to go for the entire domain of the function. This is a polynomial. My domain's from -infinity to infinity. And those critical numbers are going to go on the sign chart. If we had any vertical asymptotes or breaks in the graph, we would put those on there as well. And then we're going to test values. All I care about is is this a positive or is this a negative? So I'm going to use that factored form to help me do that. I'm going to pick a number in this interval. So let's pick x is a -2, and we're going to plug that into my derivative. Now it's going to be easier to plug it into the factored form of the derivative. So we're going to have 3 times -2 minus 3 times -2 plus 1. So I have +3. I have a negative that comes out of this parenthesis set, and a negative that comes out of this parenthesis set. So a positive times a negative would give us a positive slope. I don't care about what specific number's coming out. I care about the sign, because the sign is going to tell me if the function is increasing or decreasing. Let's do the same thing here. Let's pick some number between -1 and 3. So I'm going to pick 0. I'm going to plug it into my derivative. So I have 3 times 0 minus 3 times 0 plus 1. So I get a positive times a negative times a positive, which is going to give me a negative value. So that tells me this function is decreasing on this interval. And then let's pick something bigger than 3, like 4. So it's going back into that derivative. So I have a 3 times 4 minus 3 times 4 plus 1. So that's a positive times a positive times a positive, which is going to give me a positive. So from the side chart, we can tell what's happening to the function. So we're going to talk about where is it increasing, where is it decreasing, where do I have a maximum, and where do I have a minimum. And now we're talking about local mins and maxes instead of absolute mins and maxes. So the function f of x is increasing from -infinity to -1. In the middle is decreasing, so -1 to 3. And then on the right-hand side of the side chart, we're increasing from 3 to infinity. And we're going to join these together with the union symbol. So let's talk about maxes and mins. So if we're increasing, then we're decreasing. Then what's happening at -1 is that we have to have a maximum. If we're decreasing, then increasing, then at 3, we have to have a minimum. And if we wanted the y value for these, we could plug those x values in here and find the point that's associated with that max and min. Let's do another one. Let's use that first derivative test. So we're going to find the derivative. So we're going to get -3x squared plus 3x plus 18. I'm going to factor out a -3. And then let's factor this. So we're going to set that derivative equal to 0. So I can think about dividing both sides by a -3. So x is going to be equal to -3 and 2. So those are my critical numbers. That derivative is defined everywhere, so these are the only two that I have. So now I'm going to create my sign chart. My original function is a polynomial, so domain's going from -infinity to infinity. -3 and 2 are going to go on my sign chart. And then we're going to test values. So I'm going to pick something in this interval. So let's pick a -4. So if I were to plug a -4 in, and I'm going to use that factored form. So I have a -3 times -4 plus 3 times a -4 minus 2. So this is a negative times a negative times a negative value, which will give me a negative. Now we're going to pick something in this interval. I'm going to pick 0. So if I pick 0, I'm plugging it into that factored form again. So I have a -3 times 0 plus 3 times 0 minus 2. So this is a negative times a positive times a negative, which will give me a positive. And then let's pick something larger than 2, like 3. So I'm going to have a negative 3 times a negative 3. Oh, let's be careful. So I've got negative 3 times 3 plus 3, because I'm picking 3, times 3 minus 2. So a negative times a positive, and this would result in a positive, which would give us a negative. So compare this. So we are increasing from negative 3 to 2. That's where that value of the derivative was positive. We are decreasing from negative infinity to negative 3, and then from 2 to infinity. We will have a maximum and we will have a minimum. So here we are decreasing, then increasing, which means at negative 3, we have to have a minimum. Whereas at 2, we are increasing to the left of 2 and decreasing to the right of 2. So that has to be a maximum. Let's do one more. We want to find extrema for this one, and we're going to find increasing and decreasing also. So let's take our derivative. So we're going to have 5/3 x to the negative 2/3 minus 5/3 x to the positive 2/3. So we're going to factor. I'm going to factor out a 5/3. Both of these have an x in common, so I can pull out an x to the smallest exponent, which would be x to the negative 2/3. That's going to leave me with a 1 here, and that's going to leave me with an x to the 4/3 here. Okay, so we can always check it by redistributing. If I redistribute here, I'll get 5/3 x to the negative 2/3, and then here I'll have that negative 5/3. Remember, when we multiply and we have the same base, we add the exponents, so negative 2/3 plus 4/3 will give me that 2/3 exponent. And then I'm going to clean this up a little bit. Let me make this negative a little bit more distinct. So I'm going to have 5 times 1 minus x to the 4/3 all over that 3's in the denominator, and that x can come to the denominator and become a positive 2/3 as the exponent. So there's my derivative. So we're going to find critical numbers. To find critical numbers, we're going to set that derivative equal to 0. So we're going to have 0 equals 5 times 1 minus x to the 4/3. If I divide by 5, I have 0 equals 1 minus x to the 4/3. So x to the 4/3 is equal to 1. So I can cube both sides. So that's 1. And then I can take the 4th root. And when I take the 4th root of 1, remember I have a plus and a minus. So I'm going to get plus and minus 1 as critical numbers. But we also need to think about, where is the derivative undefined? That derivative is undefined anywhere that denominator is equal to 0. And that's going to happen at x equals 0. So that's a critical number also. So my critical numbers are going to be -1, 0, and 1. So those are the numbers that's going on my sign chart. The sign chart's going to go to from negative infinity to positive infinity. That's going to happen because the domain of this function, if I'm looking at cube roots here and here, I can take the cube root of any number. So I do not have any domain restrictions. So now let's test numbers. Let's plug in a -2. So if I plug a -2 in to test this interval, remember it's going here. So I'm going to have 5 times 1 minus x, so 1 minus oh, negative 2 to the 4/3 over 3 times negative 2 to the 2/3. I want to know, am I getting out a positive or a negative? So we know 5 is positive. I need to know what's happening here. So negative 4 to the 4th, negative 2 to the 4th is 16, and the cube root of 16 is going to be bigger than 1. So 1 minus something bigger is going to make that a negative. And then if I square that negative 2 and then take the cube root, this is going to end up being positive. If you're not sure, you could always use your calculator to type these values in. So this guy's going to be a negative. So now I need to plug in something here. Let's plug in a negative 1/2 or negative 0.5. So I'm going to have 5 times 1 minus negative 0.5 to the 4/3 over 3 times negative 0.5 to the 2/3. And I'm just going to do this off screen in the calculator. So when I type in negative 0.5, I get a positive. So now we're going to try positive 0.5. Same thing, it's going into that derivative. I got a positive when I did that. And then I'm going to plug in something bigger than 1, such as 2. And I got a negative. So let's talk about where are we increasing, where are we decreasing, and do we have any maximums or minimums? So we are increasing where we're positive, so from negative 1 to 0 and from 0 to 1. Now keep in mind the domain of this function is all real numbers. We do not have any vertical asymptotes that would split this graph into pieces. So instead of saying from negative 1 to 0 and 0 to 1, we can just smush those together and go from negative 1 to 1. Notice when we're writing those increasing, decreasing intervals, we are using parentheses and not brackets. That's because at those endpoints, something's happening. It's changing from either increasing to decreasing or decreasing to increasing. Decreasing, we are decreasing to the left of negative 1, so negative 1 to infinity, and from 1 to infinity. Again, we're doing that with the union sign. So if we're decreasing, then increasing, at negative 1, we have a minimum. And then if we are increasing, then decreasing, at positive 1 means we have a maximum. And if we want the y value, again, we could plug the y value, the x values into the original function, and we could figure out what the point would be. So let's just do one more for fun. We're going to look at the cube root of x minus 1. So we're going to take the derivative. So this function could be written as x minus 1 to the 1/3. So we're going to bring that exponent down, subtract 1 from the exponent, and I'm going to rewrite that as 1 over 3 times x minus 1 to the 2/3. To find critical numbers, we're going to set that equal to 0. And we're going to get 0 is equal to 1 when I multiply both sides by that denominator. What that means is there's no solution to this. There's no place where that derivative is going to be equal to 0. But there is a place where the derivative is undefined. It's undefined when we set that bottom equal to 0. So we're going to have x minus 1 to the 2/3 is equal to 0. And if I raise everything to the 3/2 power and then move the 1 over, we have a critical number at x equals 1. So our sign chart is going to have 1 on it. Now this sign chart, we have to think about domain. Domain for the function is all real numbers. So when I test, I'm going to test to the left and to the right. I'm going to draw a little divider there. So let's test some numbers. Let's plug in x equals 0 and x equals 2. Remember, it's going into the derivative. So I'm going to have 1 over 3 times 0 minus 1 to the 2/3. I want to know, is that positive or negative? So if I take 0 minus 1 is -1, and then I square it, I get a positive 1, and the cube root of a positive is a positive, so this guy ends up being a positive. If I look at 2, I'm going to end up getting a positive also. So what this means is this function is increasing on its entire domain. Again, I do not need to write this as separate intervals. I need to write this as one interval because the domain of this function is all real numbers. There are no breaks in that domain. This function is never increasing. Oops. And then if we think about maxes or mins, we do not have a change in increasing to decreasing or vice versa, which means there are not any.